Hello and welcome to Fernando's Corner. One of the fundamental items of optical networks is that they are linear, and we want them to be linear, which means we can take information from point A to point B without damaging the video, the data, or the voice content. This of course has been a challenge over the years, and progress in this field has been evolutionary, incremental, step by step. Cisco, however, about a year ago took a revolutionary step to creating linear transmitters, and this approach has been successful and is now part of our products. For this episode, we have our distinguished fellow here, Fred Hirt, who is one of the RF and electro-optical engineers, and he's been around linear transmitters, or the ability to make linear transmitters, for a long time. And today he's going to talk to us a little bit about the implementation of optical linearization. Welcome, Fred. We're happy to have you.
Oh, well, thank you, Fernando. You had a question about linearization.
Fred, so what are some of the mechanisms that detract from the linearity of a system, and what kind of parameters do we use to track them?
Well, glad you asked. We generally take a look at anything that prevents the output level of our light from exactly tracking the drive level of our signal. In the cable television space, we consider three such important metrics. One is the composite second order, a measure of second order or second harmonic beat products of F1 plus or minus F2 type. We also consider the composite third order, similar to composite second order, except of course for three frequencies at a time, F1 plus or minus F2 plus or minus F3 and third harmonics. And then we take a look at carriers beating against each other and inadvertently transferring modulation to a third, and that we call cross modulation. These three together are the lion's share of the analog type linearization problem.
So what are some of the techniques that we use to overcome the things that make a system or detract from the system's linearity?
Well, primarily we try to keep this line as perfectly linear as possible, but in reality a real laser will actually not be perfectly linear. So we get a little bit of compression on the top end, a little bit of clipping on the bottom. There are some techniques in the literature and in legacy products that essentially try to extend the electrical range before modulating the laser. So we refer to that as distorting the signal before it's actually used to modulate, or pre-distortion. Pre-distortion is an ancient technique. It goes back to probably the World War II era, in which it was used to increase the dynamic range of certain radar transmitters under multi-carrier operation. This has been extended in both bandwidth and in finesse over the last 20 to 25 years, and up until recently represented the state of the art.
So Fred, electrical pre-distortion or correction has been around for a long time. What is different, what is new about the optical linearization that we talk about here for our Cisco products?
Well, I'm glad you asked. Basically, every time you modulate a laser, you get not only intensity modulation, but you also get some sidebands in the optical domain. If we take a look at this as being the horizontal axis representing carrier at the optical frequency, and the vertical axis as intensity, we'll have some sidebands that exactly map on one-to-one that correspond to modulation waveform. We have a few others that correspond to frequency modulation. So what we'd like to do is see if we can get some use out of these otherwise unintentional sidebands. So to kind of refresh, we definitely create a one-to-one relationship between every modulating frequency and every sideband when we create FM by direct intensity modulation. But along with that comes this inadvertent phase and frequency modulation. Here we have a many-to-one relationship that's determined by the amount of drive that many of you have are familiar with FM and phase modulation recognize as having their amplitude set by Bessel function. The unusual bit about our linearization technology is that it operates strictly in the optical domain, and it actually uses these otherwise unwanted sidebands to self-correct the AM sidebands here. So essentially, we have a closed-loop system. We basically start by modulating amplitude sidebands in a one-to-one relationship. Any small errors that creates are in fact corrected by an optical mapping of phase and frequency modulation back onto our amplitude domain.
Fred, what are some of the products we've already introduced this technology to, and where do you think some of the opportunities lie in the future?
Well, thanks for asking. Right now, we have a product line which we refer to as the Cisco Lumen platform, emphasizing its all lightweight nature. And this platform consists of 1310 nanometer fully linearized transmitters, receiver chassis, and all the supports that go along with that. We look to extend that to our legacy Prisma 2 platform that many folks who've used scientific Atlanta equipment are familiar with. And we also anticipate applications of this linearization technology to digital on-off keying, or OOK, as well.
Well, wonderful. So friends, this is optical linearization, just a bit of a tease, a little bit of a primer. We want to thank Fred for stopping by here and letting us know all about it. I ask you to please leave your feedback on this or other topics, and we can keep the discussion going. If you have any questions that are specific, you can contact myself, Fernando, or Fred here at the Naperville facility. Thank you for coming to Fernando's Corner. Until next time.